Hi, my name is Mahmoud Nawar. I'm a senior student studying mechatronics engineering. I'm a member of the mechanical team who designed the Swift AUV.
Hi, my name is Heva. I'm a graduate mechanical engineer, class 2017. I'm a member of the mechanical team who designed Swift.
I'm Ahmed Sulaiman. I'm a senior communication and electronics engineering student, and I'm an electrical team member that was responsible for the internal structure of the propulsion system.
Hi, I'm Rafael Ayub, electrical engineer and a member of electrical team. I was responsible for localization system.
Hi, I'm Ahmed Ayman, an undergraduate computer engineering student, and I'm a software team member mainly responsible for the visual perception module.
Hi, my name is Maria. I am a senior student, currently studying communication and electronics engineering, a software team member who was responsible for developing motion control software.
Hi, my name is Anas Khamis. I am studying mechatronics engineering. I am software team member. I am responsible for motion control of AUV.
The propulsion system is a subsystem of the entire launch AUV, and its requirements must be coordinated with all interfacing subsystems, such as thruster positioning, electrical power control and distribution, motion control, and navigation software.
The electrical design was mainly focused on how to avoid any overcurrent failure and to design a PCB that can withstand high current. And so it is crucial to use current limiting and overcurrent protection elements. That's because thrusters draw high current to get decent thrust force, which will result in high power consumption. Also, the propulsion system should include propulsion controller that its main task is to handle the motion of the AUV.
For the AUV to be able to move, the thrust force resulting from the propulsion system must be greater than the drag force acting on it. The thrust force mainly affects power consumption and the battery performance. So, our design was optimized to reduce the drag force as much as possible to minimize the power consumption and save the battery's power. To reduce the drag force on the AUV, we designed the AUV to be as small as possible, and we covered the whole structure with a streamlined cover. Also, we have to calculate the power consumption of the AUV so we can select suitable battery that can drive all the electrical system.
The motion control system is an extremely important system in the AUV software, as it's responsible for keeping the AUV on the right track to reach a desired point in 3D space. It mainly consists of guidance, reference model, and the controller. Guidance receives the desired point and creates a trajectory track for that AUV needs to follow to reach this desired point. The reference model receives this trajectory track and creates states and points on it for the controller. The controller receives these states and creates the right actuation signals for the propellers in order for the AUV to move correctly on the right track, considering all the dynamics limitations and capabilities based on analyzing the AUV's motion and analyzing external forces and modeling AUV.
Since the beginning, we focused on achieving the maximum points in the competition. So our target was to design an AUV that can do the 6 degrees of freedom of motion to do all the missions easily, including the bonus missions like crossing the gate with the style. Then we built Swift that can surge, heave, and sway, and can also roll, yaw, and pitch. Therefore, we used an 8-thruster configuration, making sure that all the thrusters intakes are clear to ensure the best performance. And to achieve a stable AUV, all the thrusters were positioned precisely such that the line of the action of the resultant is almost coincident with the center of the gravity of the AUV.
We focused on Swift that we need to have high maintainability and flexibility, and so we divided our electrical system into smaller subsystems to be easy to debug. One of these subsystems is the propulsion system. The propulsion enclosure includes the electronic speed controllers, the ESCs, and the PIX hook, which is the controller responsible for the motion of Swift. This enclosure is linked to the main enclosure, the NVIDIA enclosure, using serial communication via USB. Our electrical team designed custom propulsion PCB to meet our requirements and can withstand high power consumption. Mounted on it, the ESCs, current sensors for current monitoring, and fuses for protection.
The most important aspects of our AUV Swift are its sensor fusion, computer vision, motion control, and sonar subsystem that assist its navigation. Sensor fusion is developed to minimize the impact of individual sensor failure in determining the current state of AUV. Sensors like DVL, pressure sensor, Z2 camera, and IMU. Choosing the optimal controller for Swift was important. We discovered different controllers like LQR, MPC, and multiple input, multiple output PID. And finally, we selected the model predictive control due to its predictive and adaptive nature.
Because of its importance, we decided to give a great attention to the localization. Our system based on making best use of sound characteristics. To be specific, the speed of sound. Our calculations based on the time it takes the sound waves to travel from point A to point B. So we place the hydrophones as distant from each other as possible, so we can get the highest accuracy and most reliable results. Using 4 hydrophones, those located at the corners of Swift, and the sampling rate of 200 kHz, we continuously scan the surroundings and divide the collected data into frames. Then using Fourier transform, we could find the exact frame that contains the desired frequency. Then by applying generalized cross-correlation function, we can estimate the time delay of arrival between any pair of hydrophones. Then the gathered data is then processed accordingly to determine the angle of arrival at which the signal arrived to the hydrophones. By combining the data from each consecutive hydrophone pair and by using the process of triangulation, we eventually compute the exact distance and direction of the sound source.
As the AUV's computer vision algorithms stand in the 4 navigation pile, we consider developing a visual perception module that is divided into 4 main subsystems: image enhancement, object detection, target analysis, and bias filtering. The image enhancement enhances raw images received from the cameras, sending them to the object detection node, which can detect the objects and extract their coordinates, sending them to the target analysis node, which can extract even more information, such as the AUV's orientation to the gate, which can help us align the AUV to the gate before approaching it. Finally, the bias filtering node filters any bias readings, ensuring that only true and accurate coordinates reach the local planner module.
The MPC is model-based controller, so the first development step was develop a model that described the AUV motion and the force acting against it. We started with mathematical model to obtain the correct equation for dynamic motion. Then, those equations of motion were used to develop our MPC. The second step in development was to choose and implement the correct cost function for our MPC. The cost function drives the controller to reduce the cross-track error and the normal error. Then the reference model for trajectory tracking was developed, implemented, and imported into the controller. And this model keeps track between the current state of AUV and the desired state in 3D space. During the development of Swift, we performed all kinds of testing. However, not all of us could be available on site. Due to COVID-19, the software team mainly depended on online testing, and the electrical team
was available on site to perform hardware testing with taking in consideration safety precautions. During the development, we tested our PCBs to know maximum current limit. This destructive test was done on 15 voltage DC power supply and using load blocks of various values that we added them in parallel to draw the required current for testing. We found out that at 44.5 amps, a 2.2 mm width single layer trace was burned out. At 50 amps, there was very high temperature. At 55 amps, there was a color change on a 4.4 mm width and 30 microns thickness trace. And finally, at 65 amps, the soldering came off. As a result, we enlarged the traces in our propulsion PCB into 6 mm width and 120 microns. And as for the software testing,
our controller was done using our simulator. Different scenarios were testing to increase the accuracy of our modeling and controller, and this result of sine wave as an input.
This is our first trial to test our motion control system in simulation, and it wasn't stable. This is the result after changing some modeling parameters, and we're still improving it.
Thank you for watching the video. Bye.